Here we are at the final lecture, and we're going to be covering chapters 22, 23, and 24 today. Now, it may have felt like we covered a lot of chapters last week and this week, but essentially we're dealing with things that should be so familiar to you in terms of the earth we walk on, the air we breathe, and the water we swim in and drink and everything else, that I didn't think it would be that much of a stretch to go through these different concepts. Essentially, all we're doing is really just giving you the scientific terminology as well as some of the basic reasons behind why things are the way they are. So we'll start off then first with chapter 22, the atmosphere, the air we breathe. Right? So the atmosphere is a thin shell of gases that surround the solid earth, and they're cycling materials back and forth, right? And we certainly felt a lot of it this last weekend with all of the rain. I know I did. So the atmosphere is, as I said, is a relatively thin shell of gases that surround the solid earth. The density decreases as you go higher, so that within 50% of it is within 5.6 kilometers of the Earth's surface, and 99% within 32 kilometers of the surface, right? And so based upon the radius of the Earth's surface, you get what that total volume is going to be. But I'm not going to ask you to do that. Just the key thing to understand is that it's denser here than it is. And that's why people, when they climb mountains, have a tougher time breathing and oftentimes have to carry their own oxygen with them. Oops, I guess I needed to get this onto the slideshow so that my controls work better. So, yes, so the composition of the atmosphere is mostly nitrogen. It is 78% nitrogen, 21% oxygen, 1% argon, and there's 0.03%, okay, it's about a little less than 0.03%, is carbon dioxide. There's also water that's involved there, and sometimes water is the third, it's either third or fourth, depending upon whether it's a humid Missouri day or someplace out in the desert someplace. So the trace components are water, carbon dioxide, neon, helium, krypton, xenon, hydrogen, methane, nitrous oxide, as well as any of the particles that the wind picks up and scatters across our area. So atmospheric pressure is, you can look at it from the hydrostatic view, and this is a macroscopic fluid approach. What that means is that there's a pressure is the result of all those molecules that are on top of you, okay, that are crushing down upon you and keeping you from getting out of bed so early in the morning. These are the results of the Earth's gravitational attraction, and the pressure increases with atmospheric depth. The molecular view is on a smaller scale, and here pressure depends upon the number of molecules and the force which they strike the surface. There's more molecules at the lower altitudes, and so they produce higher pressure because they're hitting the surface a lot more frequently. And how we measure that is with a barometer. It's a pressure measuring device. Mercury barometer measures atmosphere and pressures in terms of a column of mercury, and that's the standard 76 centimeters of mercury corresponds to 1 atmosphere. Now, at sea level, it's 10 newtons per square centimeter. At 5.6 kilometers, okay, and there's 2.2, let me see, what is it? It's 0.6. Divide this number by 0.6, and you'll get the number of miles high that is. So, multiply that by 0.6. So 0.6 times, that would be a little over 8 miles high. You would have this sort of a pressure. Okay? Warming atmosphere, it's heated by the solar radiation, yes. We get our heat from the sun. 50% is absorbed by the surface, okay? So the heat that comes from the Earth, much of it is coming back because it's reflecting off of the, or just giving back all of that has been absorbed. 4% has been reflected by the surface. That which has been absorbed by the surface is there and will slowly comes back, diffuses back out. 3% is absorbed by clouds, 20% reflected by clouds, 6% scattered by air. And so you have all 100% coming in, and it depends upon the wavelengths of light as well, as terms of how much of it's reflected and what it can do to your skin as well. So the infrared is re-emitted by the surface and absorbed by the atmosphere. It involves water, carbon dioxide, and water actually has a much greater greenhouse effect than carbon dioxide does. There's a lot more of it there. Losses are 20% reflected by clouds, 6% scattered by the air, 4% reflected by the surface. Now, the temperature generally decreases with increasing altitude. So when you climb up that mountain or you go to higher elevations, the air becomes much cooler. And the cooler mechanism is more pronounced at the higher altitudes. And it's about 6.5 degrees centigrade per kilometer of height that you go up. Now, the inversion is the colder temperatures near the surface. Sometimes that happens as well. Okay, so but that is not the usual case. Now, troposphere is the closest to the surface. This is where our weather is. The stratosphere, that's the temperature increases with height here, and it's less turbulent, and that's the planes try to travel in this area right here. This right here has got a lot of weather associated with it. Then the mesosphere is at the above that, and then this is the temperature decreases again as you go up, and then the temperature increases again when you get to the thermosphere up here. And you can see the number of kilometers for each of these levels. This is 10% of it right here. This is 40% of it in the stratosphere. This is 30% of it here and 20% of it here, right? In terms of strictly the distance, because it's you have to do it by it's a spherical volume going out. These are much, much larger than what we have at the surface. The wind, there's generally three motions: upward motion, movement over a region of greater heating, sinking air over a cooler region, and horizontal movement between warmer and cooler regions. Okay, horizontal movement of air is wind, but you know all of that. Local wind patterns, two important relationships: air temperature and air density. Density decreases with temperature, so hot air rises, colder air sinks, right? So the cooler air comes down the mountain, the hot air rises up the mountain. Air pressure and air movements, upward movement leaves a low pressure behind, downward movement builds a higher pressure. So air generally moves from high pressure areas to low pressure, and low pressure is usually associated with turbulent and stormy weather. Examples of local wind patterns are sea breezes, mountain winds, Chinooks, which are compression winds, and just shows the way in which these develop each time, right? This is your sea breeze, a high pressure coming in, low pressure at the land, and then circles back again. Cooler water, warmer land causes this type of a motion. Likewise, a cool surface here, warm surface here, convection moves that around. And then here you have the Chinook winds, where you've got a high pressure moving off of the land and going to a low pressure here. This is in the evening. This sort of thing happens. In the daytime, this is what happens, right? So living on the shore gives you a cool breeze almost all the time. Global wind patterns. The Earth receives more direct solar radiation in the equatorial region. Yes, down here there's more direct sunlight. Here it comes in at an angle, right? And so it doesn't have quite the effect. So the hot air rises here, rising cool air cools, causing precipitation. That's why in your central regions you get a lot more rain in there. The cooler air descends at the higher altitudes, and the high pressure belt is from 30 degrees north and south of the equator, here and here, right? So these are, the sailors used to divide these into different zones, and so they would travel, they would use these, the horse latitudes, and they'd use the trade winds, the northeast trade winds and southeast trade winds, in order for the ones for the travel. The horse latitudes were the ones where they didn't have as much wind, and then we have the prevailing westerlies here. So you've got it flows from the horse latitudes this way and then up. Horse latitudes up this way and then down, okay? And so it's really divided into some very specific regions. The jet streams are meandering loops of wind near the top of the troposphere. You can have speeds of 100 miles an hour or more, okay? So that can really help you with your jet if you happen to be flying your own personal jet up there. You save on a lot of gasoline. Water in the atmosphere. There are three phases of water. Everybody knows that. It's liquid, solid, and vapor, right? Liquid generally above zero, solid generally below zero, and 90% of the Earth's water is liquid. The water vapor is the smallest component of the three, okay? And it's one of the principal weathering and erosion agents. Just look at what happens every time we get a really, really heavy rainfall here in the Ozarks. Evaporation and condensation, liquid to gas, gas to liquid, can occur at any temperatures, depends upon the, and the vapor pressure above it gives you your relative humidity, right? So saturation means that the evaporation, there's an equilibrium between evaporation and condensation. It's influenced by temperature. Warm air can hold more water vapor than cold air. Yeah, if we have a lot more humidity during the summer months. And you can see that right here, how much the absolute humidity is. Not the relative, but the absolute. This is how much is actually in the air at any one time. The relative humidity is what the maximum is as a ratio to what is actually there. Okay? The condensation is the rate of evaporation factors, exposed surface, air, water, relative temperatures, relative humidity. That each of those determines how fast something's going to evaporate. Condensation factors, relative humidity, temperature of the air, so that if you have a cold surface out there, it's going to have a lot of condensation take place on it. You see that on the glass of your ice drink in the summertime. Water molecules join together to produce a liquid. On the surface, it's a dew. In the air, it's droplets. To produce a solid. Frost on the surface, snow in the air. Condensation, air must be saturated for condensation to occur. You've got the water vapor added to the air via the evaporation. That's why you can see your breath on a cold day, and why you also see contrails. Okay? Cooling reduces the capacity of the air to hold vapor, and so a combination of the one and two can also occur. Let's see. And dew or frost tend to form on cool, clear, calm nights. Yes, we all know about that. Fog and clouds. Fog near the ground. Clouds are higher up. The same exact phenomena. Okay? So comprised of small suspended water droplets. They form around a condensation nuclei. And the particles about which particle are falling. So that's why you can seed a cloud with certain types of materials, and if there's any possible water vapor there, it's going to start raining. And so you can actually cause it to rain. Cloud classification schemes. These are your cirrus or curly ones, cumulus, the piled up ones, the stratus are the spread out ones, right? So you see examples of the different ones there. Okay. And that's everything on that chapter. And I think we'll start and do the next chapter in a separate video. Each one of these should be fairly short. We're going to talk about weather and climate next.